So here we're trying to diagonalize matrices. Our instructions are to diagonalize the matrix if possible. And here we have a 3 by 3. It's upper triangular, so it's going to make part of the problem easier, right? So first we got to find, solve the characteristic equation with lambda in place of the x. So we're going to look at finding the eigenvalues. We'll say find eigenvalues of A. Actually, we're finding the real eigenvalues of A, you might say. So I'm going to look at determinant of A minus lambda I. That's the characteristic polynomial with lambda. Satisfying that equation. All right, so I'm going to have what? Determinant of the following matrix equals 0. So I'm going to take the main diagonal of A and subtract lambda from that. So I'm going to have what? -1 minus lambda, -2 minus lambda, -1 minus lambda, and I'm going to have the original entries everywhere else. Zeros below the main diagonal and -1, 1, 1 above. So remember that when you're taking the determinant of a triangular matrix, either upper or lower, it's going to be just the product of the main diagonal. So this makes finding the characteristic polynomial rather easy. You have what? -1 minus lambda, -2 minus lambda, -1 minus lambda, and that's all set equal to 0. This is going to give you basically 3 eigenvalues. Actually, 2 eigenvalues with one of them a repeated eigenvalue. So for example, we have what? Lambda equals -1, and we're going to have a lambda equals -2, and if you look at the algebraic multiplicity here of -1, that is 2, right? Because it's occurring twice. Let's just double check that, right? There and there. That factor is the one that's giving us -1 as our lambda value. So this gives us a multiplicity of 2 right there. And the other dude, the multiplicity of -2, that occurs just once. So that's the algebraic multiplicity. All right, so eigenvalues were easy to find. So once you have the eigenvalues, then you want to find a basis for each corresponding eigenspace. Find a basis for the eigenspace. It's not an eigenspace, it's A, isn't it? Eigenspace should be E. Eigenspace corresponding to the eigenvalue -1 of A. So basically what I have to think about, the homogeneous equation A minus -1 I times vector x equals a 0 vector, representing that in augmented form as A minus, that's not an A, is it? I said A, but I didn't write A. My E's and my A's are backwards right now. Let's see. Come on, right, please. Thank you. A minus -1 I3 augmented with the 0 vector. That's the way we're going to write that homogeneous equation. We're going to write it using an augmented matrix. This double negative becomes a plus, right? So essentially what we end up doing, we end up adding 1 along the main diagonal of A. So if I were to go back to A, when there's red diagonal entries, I got a 0 vector here on the right hand side. That's the augmented vector. Add 1 to those. I'm going to get, let's see, what am I going to get? Let's do them in red. We're going to get 0. We're going to get -1. We're going to get 0. And we add 1 to each of those red entries, and everything else stays the same. -1, 1, 1, and then 0s below the main descending diagonal. So if we reduce this, let's reduce this. I can actually multiply the first row by a -1 add to the second row, and I'll get what? 0, -1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. And we think of this as a system of linear equations, homogeneous system. Look at the general solution. It looks like we're going to have 2 free variables. Actually, we're going to have what? x1 and x3 are going to be free here. kind of unusual to see the x1 free. It doesn't happen often. x3 free is not unusual. And then we're going to find x2. We're going to get in terms of x3, so we're going to find here x2, right? And what do we got? We got negative x2 plus x3 equals 0. That's going to give us what? x2 equals x3, it looks like. So x2 equals x3. And if we put the solution, the general solution, in vector form. All right, please. Thank you. Vector form of the solution. This vector is going to be what? x1, x3, x3. In which case we can actually factor out an x1, and we're going to have coefficients, what? 1, 0, 0. We can factor out x3. We're going to have what? 0, 1, 1. So actually your base, come on, dude. Shoot. Work, man, work. 0, 1, 1 were the coefficients for x3. So you're looking for a basis here. A basis for, what do I want to call this? The eigenspace of A associated with the eigenvalue -1. We'll just call it B1. Basis 1. So it consists of these two vectors right here. Well, this time we have two vectors. 1, 0, 0. 0, 1, 1. All right, good stuff. So we got one of our bases. Now let's look at basis for the other eigenspace. The other eigenspace is going to have to do with the eigenvalue -2. So I want to look at that. We're going to find a basis. For the eigenspace associated with the eigenvalue -2 of A. All right, so let's show set up the homogeneous augmented matrix A minus -2, -2, I3, augmented with the 0 vector. So that's our A minus lambda I, augmented with the 0 vector. All right, now that double negative there, make it plus. So think about going back to your A matrix. Where's your A matrix? It's the one with the reds, and you're going to add what? Add 2? Add 2 to those entries. So you're going to get 1, 0, 1. 1, 0, 1 for the diagonal. Let's do that. One, 0, 1. Everywhere else stays the same. We're going to have zeros down the right-hand side. What was everywhere else? So again, we added 2 down the main diagonal here. We got 1, 0, 1, and we're going to have what? -1, 1, 1. See if I can squeeze that in up top. 1, 1, 1, and we're going to have zeros below diagonal. All right. So what I can do, I can put this in echelon form, right? I can take row 2, multiply it by -1, and add it to row 3. It's going to give me what? 1, -1, 1, and then 0. We're going to have 0, 0, 1, 0, and then you can cancel out that last row, 0, 0, 0, 0. Right, we took -1 times row 2 plus row 3 to get rid of that last entry there, that last pivot. Well, it's not actually a pivot, but yeah. Get rid of that 1 in row 3. All right, so it looks like here we have one free variable. It's going to be an x2. And we're writing down the general solution. The associated homogeneous system. So we got what? x2 is free. Now x3 is going to be equal to 0, right? If you take this last right here, that's going to tell you x3 is 0. But this top one here, we got to find x1, right? We're going to find x1. It's going to be in terms of x2 and x3. It's going to be what? x1 minus x2 plus x3 equals 0. Of course, we know we can plug in place of x3, we can plug in a 0. But basically, what that's going to tell us is that x1 is equal to x2. So here, x1 equals x2. So when we write a solution vector, a vector form of the solution, it's going to be a vector x. We're going to have x2, x2, and 0. Factor out the x2 and you get a single vector 1, 1, 0. That's going to be a basis for your second eigenspace. So basis, if I can spell basis for eigenspace associated with negative 2 of A. That's going to be, I'll call it B2 for basis 2. It's going to have what? This vector 1, 1, 0. So all eigenvectors can be built. So all eigenvectors corresponding to negative 2 can be built from that single eigenvector. I'm just taking scalar multiples of it. So, question, what is the diagonalization of A? So here, I'm going to write it at the top, right? A is equal to what? P, D, P inverse, where D is going to be the following matrix. It's going to be a 3 by 3 matrix. So you're going to copy down your first eigenvalues that showed up. What do you have? We have what? Negative 1. And then we add another negative 1, right? It has multiplicity 2. Negative 1 and multiplicity 2, so you copy it down twice. And then the next eigenvalue was negative 2. That had multiplicity 1, so I copied it down once. And then 0 goes everywhere else. And then you got to write your P matrix. What's your P matrix? So your P matrix goes next. It's a 3 by 3 matrix. And the first two columns are going to consist of those two vectors that we found and the basis. The basis for our eigenspace associated with the eigenvalue negative 1. So here we got 1, 0, 0, and 0, 1, 1. Say that again. 1, 0, 0, and 0, 1, 1. Let's see if I can remember that. 1, 0, 0, 0, 1, 1. Okay. So those guys go with the first two eigenvalues, right? Those two eigenvectors are associated with the first two eigenvalues, negative 1 and negative 1. And then for our third eigenvector, we have 1, 1, 0. That's going to go for the third column of P. What was it? 1, 1, 0? 1, 1, 0, yeah. So there it is. There's the diagonalization right there. Up at the top of A. It's PDP inverse where P is 1, 0, 0, 0, 1, 1, 1, 1, 0, and D is a diagonal matrix with negative 1, and then negative 2.